Hi, Jay.
Hi, Lowell. How you doing?
I'm great. Good to see you.
You too. You're
Yeah.
at home, huh? I'm in my office.
Yeah, I'm at home today. So, well,
Well,
we
you can see
appreciate
me
you.
okay?
Oh, yeah.
All right.
Yeah.
A little dark
Semester.
in this corner.
Yes.
While we're here, let me just go ahead and try to get my PowerPoint up because I had trouble with that earlier today using
Okay.
screens. Did you give me the? All
So I'm going to make you host and then you can share your screen.
right, thanks.
Okay, you should be able to.
So now I think it should be this one.
Yep.
You see
There you
that?
go. Yes, that's it.
But what happens when I put it in presentation mode? It seems to.
Well, let's see. Try it.
Yeah. So
Oh,
what?
yeah. No. Well,
Yeah.
so what we're seeing is like we're seeing the next
No.
slide view. So,
Yes, that's what happened earlier today.
well,
Do that to change.
if you go into slideshow up there at the top, let's see.
Okay.
Can you move your slide over yeah, there we go. Yeah. See, you've got it on presenter view, I think.
But shouldn't I just see? I have two screens, so shouldn't I
Oh,
choose
I
the other
see.
screen?
Can you swap screens maybe?
Well, I tried that earlier today too.
And it didn't work? Maybe Ning, do you know how?
I'll try this other one.
Okay. Yeah, so open your presentation, Jay. Yeah, there it is. Okay. Yeah, that's fine now, Jay. That's perfect.
So you're seeing the presentation part and not all the slides down at the bottom?
Yes, that's correct.
Okay, because they are appearing on the same screens as last time for me. But that's okay. This is actually what I want to look at.
Yeah. Yeah, that's so if you go forward a slide, let's see. Yeah. I believe is that right, Ning?
So what happens if I use the pointer? Do you see my pointer?
Yeah, I can see. Yeah.
Okay. Do you see my pointer now?
Yes.
Okay.
I see yeah. But go forward one more slide, Jay. See, what we're seeing is a small window. Is that what we're supposed to be seeing, Ning, or are we supposed to be seeing a bigger? Well, the screen, the slide isn't filling the whole screen. It's just filling a part of the screen, right? Okay, yeah. Okay, yeah, Jay, I think that's going to be fine. Okay.
So what does your department look like these days? You doing your classes in person?
Yeah, yeah. We are. I mean, there's still some online stuff, but for example, my class is totally in person, and I think a lot of the classes are in person.
That's true for us too.
Yeah.
I made a big mistake though. On Tuesday, I have classes on Tuesday and Thursday. And on Tuesday, I told everyone I wanted to do next week's classes by Zoom. And I went into class today and there was nobody there.
Oh, they thought it was today, you said?
Well, I mean, here's the problem. So I went there at 11, exactly at 11, and there was nobody in there. And so I immediately concluded that they had misunderstood and left. But then it turns out that they were just late, I guess. So I, emailed everyone and tried to get them on Zoom today, and I got about half of them.
Oh dear.
So if I hadn't mentioned anything about Zoom, we would have had a normal class day.
Oh dear.
And also, if I just stuck around for a few minutes, I mean, they're supposed to be there at 11, and they usually are.
Yeah. Just one of those things, huh?
Yeah.
Yeah.
Mhm. Oh, really? For every class? Mm-hmm. 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 Yeah. I have this one student in my class who's come to just 2 or 3 classes and only handed in one homework assignment. And I don't really care, but I worry about him, if he fails and then complains later. But I gave an exam last week and he got the second best grade. So
Wow.
I don't have to worry about him now. Also,
Yeah.
probably goes to show that whatever I have to say doesn't help anyone do well in the class. No reason to come to my lecture.
Oh, I don't know. I still think the face to face is just the way to go. It's so much more engaging.
Yeah. Yeah, mine is completely different material. I don't do anything that's in the book. I haven't even read the book. I I assign them reading out of it and I assign them problems to do out of it. But what I show in class is completely different.
Wow.
Um, okay, so that's the time.
Um, I don't know how to do, I don't know how to do that. Yeah, Mortaz is in class right now, I think. But let's uh yeah, I'm surprised he's not on yet. Let's see if he's no well, Mortaz sent a reminder a couple days ago. So mhm. Well, we'll just wait a few more minutes. Um, but there's usually some late comers here.
There are a lot of things I like about Zoom. I've decided some things I don't like, but one thing that's good is that people can just leave whenever they want to and doesn't disrupt anything.
So you guys don't use Teams?
We do use Teams,
Yeah.
but mostly Zoom.
Okay.
I seem to have a problem with Teams. When I'm at
Oh, do
home
you?
with my Mac, it just starts burning up the CPU and then everything slows down. Don't have that problem with Zoom.
Let's just wait a few more minutes, Jay, if that's okay with you.
Sure.
I know your time is precious as you know, But normally we have, we've been averaging about 30 folks, you know, and I know Bob is teaching and he has a class right before this, so he's usually late joining. Dr. Longley, is he here today? You were, oh boy. Do you have the link? Okay. All right, Jay, we apologize.
That's no problem.
Okay. Okay, here's some more joining. Yeah, and I'll give you just a real brief intro, Jay, and then I'll let you take over.
Okay.
I saw the flurry of emails about the NSF proposal, so
yeah, it's a ridiculous thing to have to worry about. Bob's right about that, but I don't think his solution is a solution.
Yeah.
But we should start having meetings pretty soon, or at least just to get organized to start with.
Yeah, I think that's a good idea. Those meetings were quite effective, I thought.
Yeah, I thought so too. Really helped us focus.
Yeah.
I meant to send around a doodle poll today, but I forgot to do it. I'll try to do it this evening.
So Ning, you resent the link? All right, that's time is, yeah. So Jay, do you guys have a weekly seminar?
Yeah.
Yeah. Is it online?
We're not doing it. Well, it depends on the speaker right now. We intended to do them mostly in person this semester, but a lot of the speakers aren't coming, so we'll do them online then.
Yeah.
Actually, it's always an option for the attendees, which is good. I usually drive back to Austin on Friday and often tune in.
Oh, okay.
Also, it strikes me as the least good thing to do, you know, with COVID, cramming ourselves in that room.
Right.
Everything else, we have a chance to spread out. I have only 7 students in this class, and you know, the room will hold at least 35.
Yeah.
During the seminars, we fill it up, 100 people or so. Maybe not.
Okay, well, we're getting more people joining now, Jay. So I would say we're going to go ahead and get rolling to honor your time commitment. So I'd like to welcome everybody to today's seminar. And we are very pleased today to welcome our good friend and colleague, Dr. Jay Pulliam. Jay is currently the W.M. Keck Foundation Professor of Geophysics at Baylor University. And Jay received his PhD from University of Cal, Berkeley. And his research interests include solid earth and planetary sciences, specifically geophysics and seismology, tectonics, and energy geoscience. So with that brief introduction, Jay, thank you for your time, and I'll turn it over to you.
Okay, thank you very much. And thanks for the invitation too, to talk with all of you. I had a hard time picking a topic, and as you'll see, I kind of punted on it and chose a couple. So I think it actually may work okay for a forum like this, because anyone's free to tune out whenever they want to. You don't have to stick it out. But the first part, I'm going to talk about a couple of applications in seismic interferometry. And there's some challenges that this new type of seismology presents to us that we didn't have to confront with more traditional seismology. Let me just say while I'm here, so these are the 2 titles of these talks. The second one is really kind of a proposal, just an idea. And I'm looking forward to any sort of comments or input I might get about that. True for the first part too. I'm just going to throw out a number of issues that and our solutions with how we dealt with them, and any comments would be more than welcome, either during the talk or afterwards. So I put this up here just because I spent a sabbatical semester at this Indian School of Mines in India, and I also used that time to go around and talk to a number of people, different institutes, about this idea of the Northeast region, the Shillong Plateau, and what's happening underneath that plateau with crust beneath Bangladesh, and tried to drum up some interest in starting a big project there. But COVID kind of got in the way, so it's still just kind of an idea that we're batting about at this point. Okay, but first to seismic interferometry. So I'm going to contrast that with traditional seismology, which is sort of a distance equals rate times time problem. The exploration implementation of this, or active source, is one in which we control the characteristics of the source, the frequency content, the location, the number of sources, and all the the sampling interval of the sensors and the spacing of the sensors and everything. So we have a lot of control about how to design the experiment. With seismic interferometry, we don't, because we don't really know anything about the sources. We just put out a bunch of receivers and we record ground motion continuously, and then we try to identify the waves that are sweeping across the array and do some processing to improve the signal to noise and try to use those for imaging. So this is a pretty famous figure at this point that kind of illustrates the idea with a numerical experiment. You've got two receivers, XA and XB, and then you've got a whole bunch of sources distributed randomly, but also pretty comprehensively around them. And if you plot the cross correlations of the arrivals at these different, at these two receivers as a function of azimuth, so here's azimuth on the x-axis and amplitude, what's the time difference between the arrivals at the two sensors on the y-axis, you'll find that if you look at, say, negative 90 degrees, you'll have an arrival with a certain polarity, and over 180 degrees away, you'll have the same amplitude pulse with the opposite polarity. So that when you sum across all azimuths, so that's this here, those will cancel out, and you'll be left with these two extremes, here and here, and those fold back on each other. So you could just fold that around the 0 point and reinforce this. These just indicate waves traveling in opposite directions across these two sensors. So that's great, and that works in many implementations, but there are some challenges. One is that in the real world, sources are not distributed evenly like that. And so we have to confront that problem. Most of the sources that we use in sort of regional scale studies are microseisms, meaning their interactions with waves at the coast. And so different places inside the continent will have very different characteristics, both in terms of amplitudes of the waves and the directions of propagation and everything. So here, for example, in Waco, we have most of the energy coming from the southeast, the Gulf of Mexico. Okay, so we have to deal with that. Another is that surface waves dominate the recordings of ground motion, because most of the sources happen at the surface of the Earth, and they're not efficient producers of body waves. Body waves, travel through the body of the Earth or the subsurface, and they give us the real high resolution, high frequencies that we need for high resolution imaging. So we don't really want the surface waves, and yet they dominate the records. So the other thing is that when we're setting out a bunch of receivers, a deployment of geophones, we need to make a lot of decisions about the sample interval, the spacing and everything, and also how long to leave them out and how to orient the array and everything. And we don't, in the absence of any information about the sources, we don't know how to do that. And another is that these waves tend to be very low amplitude. And so we have to record for a long period of time and do the processing over different time intervals, different windows, and stack those to improve the signal to noise ratio. But we don't really know how long we need to do that for. Another thing is that when we do this sort of thing, now these sensors, really high quality sensors like nodes, are inexpensive and typically have many, thousands of them. And they record continuously at high sample rates. And so they're huge volumes of data, and we can't use traditional techniques to look at them. It's just too time consuming. So we need some techniques for dealing with these large volumes of data. So just in case you wanted to end the day early, I'm going to give you my solutions to all of these things right up front and then give you some more details afterwards. So for the uneven distribution of sources, there's a technique that's been used in all kinds of wave propagation problems, including radar and many other things for decades and decades. It's called beamforming. It's basically tuning the array so that it's more sensitive to waves coming from a certain direction. And we have an unusual, case here because we need to do double beamforming, meaning that we want to tune in that direction along the axis of the array and also back 180 degrees in the other direction along the axis of the array. So we want to do double beamforming. Next is to find time windows that are rich in body wave energy and have relatively little surface wave energy, and then selectively stack those. We have many examples that show that this fairly standard brute force to stack, process and stack everything approach doesn't work as well as finding windows that have relatively low noise or contaminations like surface waves, and selectively stacking the ones that are best. So the challenge, of course, is how to identify those. And then about the data acquisition plan, if we could do this sort of processing in the field or at the edge, as my student who's really good at coming up with buzzwords describes it, we could, in principle, reconfigure the deployment, that we could redo the spacing of sensors. We could, reorient the array, all sorts of things. So if we could actually get some results, and also we would know when we have reached convergence, and we could pack up and go home confident that we've gotten the data we need to solve this problem. And then the huge volumes of data need to be addressed in some automated fashion. We need some kind of tool that will perform some of the basic assessments and processing without our intervention. And for that, we use machine learning. Okay, so there are some limitations we're not going to overcome. And one is that most of the waves that we get are not really sufficient for imaging purposes. They tend to be too low in frequency or too narrow band in frequency. The Earth is a low pass filter, so we're talking about microseisms at the Pacific coast, for example. This can be a very low wavelength signal that arrives here in Texas. Another is that I've already mentioned the surface waves overwhelm the body waves, but that's because body waves are very low amplitude. And so we can do everything, there are various ways we can filter the data to remove the surface waves, but if there were no body waves there to start with, we're not going to be much better off. So I don't really have any suggestions for how to deal with this. I'd be happy to hear some ideas. Okay, so one thing we did was we got a grant from the Department of Energy to actually build some hardware, build a tool, a smart array that we could use to acquire and process the data in real time. So these are independent nodes, and we actually use some legacy equipment, these RefTech. I also want to emphasize this is a proof of concept. We just promised to show that it was possible, and we did everything we could to build this array and write the software so that it would work. We didn't learn anything significant about the subsurface in our various tests, but we did show that this is possible and will work. So don't get too excited about results. Okay, so the keys to this were using this RefTech broadband seismic digitizer and recorder. That's was made by RefTech there in Plano, I think it is, or somewhere around Dallas. And there are thousands and thousands and thousands of these things around the world. This is the standard tool for broadband seismology that I've used for many years. And so the problem is it's kind of old-fashioned now. It does a good job at what it was intended to do, but we can expand its functionality considerably if we add something like a Raspberry Pi processor, which is a little $35 processor, to it and program that thing to pull off the data every now and then stand up a Wi-Fi network in the field and send the data around. Because when you do these cross correlations, you need to have a complete data set at every node. So each one of these is attached to a sensor, and each one is attached to a Raspberry Pi, and then we have antennas. This is just one of the first tests. We ended up with 150 nodes. And then we do distributed processing. Each of these things computes its own virtual source gather for data that this geophone participated in. And then there's a time lag. So I said real time, but it's really in near real time. And over the space of a few days, you'll slip by some hours. And by the end of about 10 days, we were almost a day behind. But still, we're getting results along the way, and we can see A, that everything's working, and B, that we're getting the kind of, the design parameters and the configuration of the array is appropriate for what we're trying to do here. So yeah, it was actually a big effort then to get all these things together. One thing we didn't do was make a nice little package out of them. Each of these we put into a big old box, and so they all had their own batteries and everything. So it turned out to be pretty difficult to move these things around. But of course, one could redesign, one could build an entirely new instrument. In fact, things like this do exist. That's much more compact and lightweight. So this is a test we did out at a geothermal field, an existing geothermal field in San Emilio, Nevada, 2019, and we got some results. These are mostly direct waves here. I'm going to show you some better results later once we went home and came up with some new algorithms. So one thing I skipped over very quickly, and I remember when I was writing this proposal that I was really afraid of all the bookkeeping that was going to be necessary with getting all the data to the right place at the right time. And I was very happily surprised when this student suggested we use this decentralized database called Cassandra. It's invented, I think, by Facebook and is used by Netflix now. And the idea is that it will reproduce, it will ensure that there's a complete copy of every piece of data at every location you specify. And so it basically solved this whole problem for us. And it was a huge boon. And I highly recommend anyone wants to do anything like this, that you look into this. It's there's a public domain version of it now, but there are also a couple of companies that have adopted it and are continuing to improve it and charge a little bit of money for its use, but we just use the public version. Okay, so this worked pretty well. The keys, of course, were having enough horsepower. It didn't require much memory, but we have to have enough computing nodes that we can be running these cross correlations and stacking at all times. And to do that, we used, we tried a number of different processors. I'm actually sparing you an awful lot of the details here. It turns out the Raspberry Pis, particularly the newest version of the Raspberry Pi with 2 gigabytes of RAM, did a really good job. Okay, so what we didn't really do is assess the array's utility for determining whether or not we've reached convergence. And so to do that, we tried to compute a number of different features of the time series. And again, sparing you an awful lot of details, we discovered that 2 of them do help us identify individual windows that we can then stack for a total of about 25% of the data and produce a better result than if we had stacked all of the data. And so the way these things are usually done is you have a time window that you have to specify. For us, it was 5 minutes. And so these are each 5-minute intervals starting at different times over a few days. And then each of these is, here we go, RMS energy. So this is one of the features back here, RMS energy, which is just like the root mean square of the whole time series. And then there's also skewness down here. Skewness is a measure of the tailedness, or some people say peakedness of the distribution. So you pick out the best scores and you stack what turned out to be 25% of the total. So the top quartile. And that allows us to identify some body waves here and here and here, which didn't show up in that original virtual source gather. Afraid I don't have the side-by-side comparison here. So that worked okay. One problem is that, so we were able to identify by laborious, trial and error with this data set. There's nothing saying that there's no guarantee that these particular features will be successful in the next implementation. So that's not really a satisfactory solution. It did work okay in this case. I think I've said most of these things before. Those stacks I showed were the result of stacking 25% of the data. So selective stacking, as I claimed at the outset, is the key to getting a better result. And one could do it after the fact, after you've gone home and done all this processing in your lab, but then you'll never know for sure if you could have done better if you'd stayed out there longer. Okay, so this array does have a lot of different applications. It was funded particularly for seismic studies of the geothermal area. Seismic is often not so terribly helpful in geothermal exploration. Anyway, so there are a lot of other applications that may be better suited to anything that just requires, fairly consistent computing over a period of time. So for 4D monitoring, for example, or anything that requires additional computations that can be automated. Okay, and so the next example could have been applied to that same data. We actually applied it to data from an array that was deployed, not by us, but by other people near Sweetwater, north central Texas, in 2014 for about 3 weeks. And it was a pretty big array, but one of the assumptions of this processing is that the velocity is consistent underneath the array. So we used a subset to try to satisfy that assumption. And found some pretty cool features. We're just trying to come up with a technique that would allow us to automatically identify time windows that produce a better result than stacking everything. So once again, same problems last time. So just out of general interest, this is what, these are time frequency plots right here. Here's time, here's frequency, up to 250 hertz. And so there are a number of features that we identify just by eye in here and by some ground truth. The one thing we weren't really able to confirm was the signature from wind turbines. Turns out most of the wind turbines around there, and there's a huge number, but they were installed late in 2014, right after this array was there. So there probably were some in here. We just don't really know what they look like. But here's a pump jack. You can see a very regular signature. Here's an airplane. It's a Doppler effect. This is fairly close to 2 airports, with the Lubbock Airport and the Abilene Airport. And then here's vibra-size sweeps. So those are things, well, the vibra-size, of course, would be good, but the rest of these things are not particularly good sources and play no particular role in this processing. But the idea is to identify a number of features. Here's the one that won out in the end. It's this frequency domain amplitude. So it's just trying to identify the locations of high amplitude waves at various times. Probably can't see the scale, but yellow is high and dark green is low. And so that allows us to identify the locations and time windows of good sources. And this algorithm will cluster them together, and you can pick a couple of different of those clusters for processing. And here's one that worked out pretty well. Here's the stack with all of the data together, and you can see that this doesn't really show up in there. So this is the brute force. It's kind of the naive approach where you just process and stack everything you record. And here's the selective stacking results for two of these different clusters. This one didn't work too well, but there's other stuff here. Okay, so that's pretty hopeful, and that's something that is adaptive. That one works. It's easily automatable. I thought I had a little conclusion slide here, but I guess I don't. And that one could easily be implemented in any sort of array or automatically. Okay, and then here's a surface wave example I wanted to talk about, because this is the beam forming that, especially when we're talking about large scale studies, this is on the scale of the southeastern United States. These are broadbands from the US array deployment. This is all the instruments that were available circa about, I can't remember now, maybe 2005 or something like that. So you can see that back in the day, this was not something we could do, but thanks to the TA deployment, we have a lot better coverage. Here are all the stations that we used in this particular study. So this, again, is looking at surface waves, almost certainly Rayleigh waves. And rather than assume or hope that the sources were evenly distributed around each station pair, we apply this double beamforming technique for each pair of stations. And essentially, it's a delay and stack technique that essentially, if we're looking, say, at this, I will show some results for this particular array in a minute. So it will admit data within a user-specified angle of this, the axis of this array, both in that direction and that direction, and reject everything outside of it. And I can show you a pretty dramatic result. This is just the ray coverage we get for these different station pairs. Okay, so this is not as good as I had hoped. But this is a cross-correlation. This is kind of a standard technique. This is cross-coherent, which is really similar. It's just a different way of normalizing the amplitudes. And you can see out here at 400 kilometers distance, you do get this arrival, but it's much more dramatic in this example with the beam forming. So that's partly because it doesn't really look like it here. Okay. And so that has consequences. If we form the surface wave period maps for group velocity for both these, the results, the dispersion curves that we compute for both these different techniques, we get, so here's the one with the cross correlation. This is, let me show you over here first. The dramatic difference between these two is right in here, where we get a low velocity corridor that pretty closely corresponds to this location that was proposed recently. I think it's 2017 or 18 by Boot and Knapp from an offshore survey for this Suwannee suture. So this is basically the docking point for the African crust Gondwana during the Allegheny and orogeny dock with the Parentia. And it turns out some other studies have indicated that it's a very shallow dipping thrust with a detachment fault right around in here. So that's actually a better indication. And by the way, this is for 25 seconds. And 25 seconds has a peak sensitivity of about 20 kilometers, maybe 15 to 20 kilometers depth. So that's kind of mid-crustal, mid-lower crust. That's where this detachment fault is located. So this makes good sense, and it doesn't really appear. You could argue that it's there, but it's not nearly as clear with the cross-correlation results as it is with the cross-coherence and beamforming. All right, so this is not exactly ambient noise, but this is just an application that I was very happy with because it fixed one of the bigger mistakes I've made in my career. This is an onshore-offshore study I did with folks at UT Institute for Geophysics. They did the marine part here. This is a bunch of ocean bottom seismographs and a marine seismic ship. We did the onshore part. We put out broadbands for about 3 years. over 290 kilometers. And then we also put out 400 of these Texan sensors. These are 4.5 hertz, just single component geophones, just for a few days, and shot this with the seismic ship. And we were hoping these are extend all the way 107 kilometers. I thought it was more than that. And it turned out we got almost nothing for a couple of reasons. One is the sediments were more attenuating, scattering than we expected. Another thing is, well, I think the air gun array was underperforming as well. And then the other reason is that it's hard to put these things out very quickly. We put it right along the roadway. That's the way you almost always do it, because it all has to get out within a day because of the short battery life. And it's easiest that way. Problem is that we shot this the day before Thanksgiving, which is the most heavily traveled day of the year. And when we got the results, we have this one section, which is private property right next to the coast, and you can see the air gun shots very clearly. But pretty quickly, you get into this mess of cars. These are all cars on the highways. And so you quickly can't pick these things anymore because they're overwhelmed by these huge waves. So we cross-correlated those, and we were able to identify the direct waves, the body waves coming from those air gun sources, and we could then combine those with some other types of data. I'm not going to really go into this, but this is a refracted wave, travels horizontally in the upper mantle just below the moho from regional events, and it turns out there are a number of repeating earthquakes near Snyder, Texas, which is kind of on the axis of this array. And so those have very different wave propagation ray paths than the PG. And then we also used teleseismic waves from very distant earthquakes on the other side of the world, a couple of different types, including this particular SSPMP phase, which has a ray path. I'm sorry, I didn't show you the ray paths here, but it comes up, converts from S to P, and then reflects off of the moho and back up to the surface as a P again. So it gets it's a reflected phase on the upper side of the moho. So these are the ray paths. Here are the ray paths in the sediments recorded by that Texan array from the air gun shots offshore. And that provides very strong constraints on the velocities of those sediments. Otherwise there would be a pretty strong trade-off of these nearly vertically propagating waves. It produces this high velocity anomaly in the crust right at the coast, which corresponds with a magnetic anomaly there. Okay, wow, what time is it? So that's kind of the end of the seismic interferometry bit. I thought I intended to go back to this original slide where I claim to have solved all of these problems. Didn't put it in there. Double beamforming I showed with the surface waves for the southeastern United States. The selective stacking came up in a couple of different cases, including the Santomedio data we collected with the Rapier array and with the Sweetwater array. And yeah, we never ended up, well, we did 4 tests. We did 2 here in Waco, and then 2 different geothermal sites in Nevada. And in one of the tests, we did end up moving the sensors around a fair bit. But for the others, we didn't actually. But in principle, one could. We get these results every hour. We're spitting out some diagnostics and assessments. And one could go back and reconfigure the array if you felt that was necessary. So assessing the convergence, yeah, I didn't actually talk too much about this, how to do that quantitatively. We basically found ways to do it automatically, and then subjectively looked at them and decided this one was better than that one. And then identifying what features are useful and are best to participate in this selective stacking. I think we're just finishing that up now. Well, it's not going to be finished. We're finishing the manuscript. Okay, so anybody have any questions about that? Welcome to wait Nope. Okay, here's a very abrupt change of gears. Makes no sense whatsoever. I'm doing it anyway. So this particular area in Northeast India used to be a neighbor of ours some time ago. And then after this breakup, this
Hey,
portion,
Jay?
yeah.
Sorry, just I was trying to find my controls here. You know, when you showed that map, you compared the cross correlation with the cross coherence. You showed the map and
You want to go back to that?
matching that. Yeah, can you go back to that slide just for a second? Yeah, that's the one.
Mhm.
And you showed the nice match with that dash line on the right-hand side, cross coherence. I was noticing on the left side, the cross correlation, there's a lineament there over on the east side between yeah, exactly. Is that real or artifact, or what do you think about that?
I don't know about that. It does look like linear, and there are some basins here, but they don't really have that shape as far as I know. I'm not sure quite what to do with that, partly because it's not quite the same over here. It does persist for the different periods. It becomes broader for the longer periods, as you'd expect. We're still kind of puzzling over this right now. I think this is the main result of this work, and I'd be happy to hear any sort of comments. There are a couple of other features, you know, we'd really like to look at. The Wiggins Arch down here, it's just not resolved because of the coast. You know, we don't have enough stations.
Okay.
I mean,
yeah, it just caught my eye, so I'm just curious what you thought about it.
Yeah.
Thanks.
Yeah, I don't know what I think about it. Okay, so after breakup, this peninsula that is now India started charging northward at a very rapid rate and collided with Asia, and it's still moving northward. So here's this particular region that I've been interested in for quite some time. Then I spent that sabbatical. This was many years ago, 2007. We tried to get a project going here. But in 2019, I spent this time in India, and I went over and visited and had a look at some of this stuff myself. It's really dramatic. This Shillong Plateau is very high. I haven't thought about this for some time, so none of these numbers about its elevation or anything are going to roll off my tongue. But it's a real high standing plateau. It's a really dramatic drive up from Assam up to the top of the plateau. And it's the site of two great earthquakes in the past, I guess it's more than 100 years now, 120 years, one in 1897 and one in 1950. And the thing that's crazy about the 1897 event is that there's no surface rupture. This thing supposedly went up vertically a huge amount. I would get it wrong if I tried to guess, but many, many meters. And that survey seems to have been pretty well done. Remember the headquarters of the British Empire in India was in Calcutta, right down here. And the head of the British Geological Survey at the time, Oldham, went up and did this survey afterwards. So those data, I think, they were reinterpreted recently by Roger Pulliam in a paper. So, but still no surface rupture. So that's kind of nuts. And then what else? Well, there's been a flurry of papers recently about the northern Bay of Bengal, which is down here. By the way, whenever we talk about the Gulf of Mexico sediments, we always talk about how it's the second deepest pile of sediments on the planet, right? Well, this is the deepest, up to 20 kilometers right here. So it's really dramatic. And so there was so there is a thrust fault here that bounds the southern edge of the Shillong Plateau, east-west trending. And then there's also subduction here underneath Burma to the east. And then, of course, the main Himalayan thrust up here as well. So there's definitely compression here, no question about that. In fact, the point of Billam's paper is he called this pop-up tectonics, where this is squeezed and it's, you know, a volcanoes terrain or something. I don't think anybody really knows what it's made of or where it's from, but it's different from everything else. And so it's being squeezed and it pops up along these faults. The question is why? And so there was a series of papers that came out starting in 2016. Sorry, this is 1989. This is the first suggestion that this might be oceanic, this northern Bay of Bengal and the crust underneath Bangladesh. And then, okay, so there's a refraction study, very high quality, but the problem is that it's too far to the east, and they did have a couple of stations in Bangladesh, but they didn't really use them. And so it represents the structure underneath West Bengal, the Indian state of West Bengal, which is continental. So, but still, there's back and forth. So it's either oceanic, continental. There's a paper from a marine seismic study where they suggested that it was continental crust based on something I'll show you in a minute. And then Manik Talwani and some colleagues made a comment on that, in which they called that into question, actually even using figures from that very paper, and said, no, it's not continental crust, it's oceanic crust. Sibue and colleagues were not convinced, came back again, said, nope, it's thin continental crust. And so Talwani and colleagues published a full paper in which they made their case that it's oceanic crust. They still were not convinced, continental crust. And then a couple of papers that don't have comparable data that sort of addressed but didn't really resolve the issue either. But I think there's good reason to believe that it is oceanic crust. And the question is, what are the implications of that? And I think one of the implications is that that oceanic crust beneath Bangladesh is subducting, has just begun to subduct underneath the Shillong Plateau. And that's the reason the Shillong Plateau is being thrust up. And there's some other issues. Well, so there's some good reasons why it's been overlooked to this point. The main one, of course, is that there's incredibly deep pile of sediments there. It's just, and also there hasn't been any real science done there. Okay, so the argument Sibue et al. Used was that if you plot the velocities of oceanic crust versus continental crust, even stretch continental crust, you find, or at least they claimed, that their observations were closer to continental crust. So this is sort of interspersed. This is a paper by Aaron Singh from stations deploy, broadband stations. This is with receiver functions. So this is a little bit different. I think he did an excellent job here of all the analysis and then misinterpreted the results. So this makes sense that you've got Moho down here. This is about 30 kilometers. You have to remember, though, there are 20 kilometers of sediments on top. So this is not necessarily thick continental crust. It's just depressed oceanic crust, possibly. But he concluded that it was continental crust. And one thing that was a little odd is that when you do these receiver functions, if you look at the transverse components of the receiver functions, they will indicate either nothing, meaning that it's isotropic and more likely to be continental crust, or you could get a certain pattern that could be produced either by a dipping structure, like a subducting slab, or anisotropic material, which, like oceanic crust is highly anisotropic. So these are, he even showed these in his paper, these the transverse receiver functions, and I plotted them up like this. So the black ones are isotropic, the red ones are anisotropic, and they're not exactly separated. Can't remember what blue meant. But by and large, the ones that show anisotropy are out here in the flatter part of Bangladesh, and the ones that show isotropy, fail to show anisotropy, are in the more steeply dipping part of the subducting slab beneath Burma. So he concluded that these, we should, well, he didn't have, I don't remember what he did. He didn't really comment on the anisotropic characteristics, I don't think. But to me, this is evidence that this out here is probably oceanic crust. It's not dipping, but it is anisotropic. So it means the material, it shows this pattern. So the more likely interpretation is that there's an anisotropic material in the crust, and that's probably oceanic crust. So that's, and then Talwani used the same figure that Sibue et al. Had used and claimed that no, the profiles that they found were actually more like oceanic crust than continental crust. So that's part of their argument. Another part of their argument is that they've got these two traps, the Silet traps and the Raj Mahal, and they are contemporaneous and have the same chemical signature as their Kerguelen eruption. And so he interprets that, and they're connected by this magnetic anomaly, which is also this right time period. And so his claim is that this is the leading edge of the oceanic plate that's separated from Gondwana. And so this all was very exciting to me, and I went around and tried to convince people, including at the National Institute of Oceanography and GOA, that we should mount a big international expedition here and try to use some of these techniques, seismic techniques, to address this. And then this paper came out, which, you know, other people had been thinking about this subduction as well, which I find very convincing. I'm not seismologists. Again, there's no more seismology in here, except there's some focal mechanisms, which I find to be, you know, they're pretty jumbled. Also, I'm not used to looking at them on the side like this, but there are thrust events down here. These don't look like thrust events. But this is through a variety of arguments, and I can't do them justice now. They also claim that this is the oceanic crust, Bangladeshi crust, subducting underneath the Shillong Plateau. By the way, this thrust zone that bounds the southern edge of the Shillong Plateau is called the Dalki thrust. And so this is the cartoon that they published without any real imaging to base it on, but it's just the argument. And that plays into this, this middle Himalayan thrust. Okay. And I guess some GPS data showing that the Shillong block is being thrust nearly backward. Sorry, I haven't thought about this in some time. I don't remember exactly what these arguments are. And so here's the thing I find pretty motivating, though, is that, yeah, so you've got this, okay, transitional, but it's oceanic crust, and there's heavy sediments on top, and that's why the Moho is sort of a typical depth for continental crust, but it's not continental crust. And so it's subducting underneath here. That's a significant part of this compression that's taking place here that is being, you know, satisfied partly by this the Himalayan thrust, but also partly by this. Oh, that's what it is. So they have some you know, evidence of the shortening that's taking place over I don't know what time period, and so they claim that there's just too much shortening, and some of the crust must have disappeared. And then the other part that I don't have any figures for is I went to the Indian AGU equivalent and talked. Well, first I saw a presentation and then talked with someone who does surface wave inversions from someone I can't remember what university she's from, but she showed me some great results for this region as well. Again, it's surface waves, so you don't have great lateral resolution, but it shows what she was interpreting to be a root underneath the Shillong Plateau. But I think rather than a root, it's actually the leading edge of that oceanic plate subducted underneath the Shillong Plateau. So all that kind of makes sense. Oh, and I think that these Malik et al. Also satisfied that vertical uplift that was implied by the you know, triangulation data from Oldham et al. So all that kind of hangs together, makes sense. It still does not explain why there would be no surface rupture. By the way, this fault that just because there's a bounding fault on the southern edge of the Shillong Plateau, people assume there must be one on the northern edge as well. And because Oldham discovered or studied this, nobody discovered it. It's often called the Oldham Fault, but no one has ever seen it. There's no surface trace. There's no evidence for it whatsoever. So that's another big mystery. How can you get such uplift with no surface rupture? And it was a magnitude like 8.9 earthquake. Of course, there were no magnitudes at that time, but it's been reassessed. It was a very, very significant earthquake. So my basic suggestion was we should do something like what we've done here in the US. And by the way, I tried to put together a talk in which I compared and contrasted the Gulf of Mexico with the Bay of Bengal, and I realized they're mostly different. It wasn't a very useful organizing principle. But something like this, a couple of transects, and the problem, well, there are several problems. One, of course, is that we require international cooperation between India and Bangladesh, which is difficult to pull off. Another is that Indians are really tight with their data, won't let any geophysical data get out of the country. So all those things are surmountable. The thing that, at least in the short term, was not really, that stalled all progress on this was the COVID pandemic. So, and I think one thing I neglected to say earlier was that a lot of this imaging in the middle and eastern United States, needs some of these innovations, because typically the way we've done it is with earthquakes as seismic sources, and we just don't have many earthquakes around here. Another thing historically is that, well, most broadband seismic stations are installed for purposes of monitoring earthquakes and estimating and mitigating seismic hazard, and everyone acknowledges that we don't really have seismic hazard, nothing significant around here, or historically haven't. So we've been under-instrumented compared to the Western United States. But even with the instruments, we need some other techniques. So I think that's all I intended to say. I do need to give credit to people. I think I hope I cited some of the work along the way. A lot of it was done by graduate students. And of course, IRIS is very helpful. They supplied me with the instruments and they archive the data and allow us to slice and dice it the way we need to. And then a little bit of funding, none from NSF on these projects. So I had them on there and I erased them. So that's all I really intended to say. I'd be happy to take any questions or engage in any sort of a discussion.
Okay, well, thank you, Jay. Are there any questions? If you have a question, you can either unmute yourself or you can type it in the chat room and we'll relay it.
I've got a question, Jay.
All right.
Or comment, really. I mean, I see that you've got a thrust fault on the south side of Shillong, but that doesn't make it a subduction zone. I mean, no. That's just a thrust fault, so don't want to get carried away. The other thing is, if you think about the geothermal gradient in 20 kilometers of sediment, assuming a 25 degree per kilometer, that's going to be 500 degrees centigrade at the base of that pile, which is going to be, close to amphibolite facies metamorphism. So, it's going to look even more like continental crust, or like, for that matter, depending on the nature of sediments, oceanic crust. So it gets to be a real problem using what we know about continental and oceanic velocities, which have been worked out for things without that much sediment on them, to apply them to stuff that's, down at 500 degrees centigrade. And I don't know how you attack that, but we also have that problem for the Gulf of Mexico. You see what I mean?
Yeah, I see what you mean. Well, do you think it's an interesting problem? Do you think it's something we should
Oh,
study
no,
further?
I think in the 21st century, there's a lot of thickly sedimented basins, Gulf of Mexico, Bay of Bengal, and I include Bangladesh in the Bay of Bengal, Aleutian Basin, there's Caspian Sea. Those are interesting problems. And, you know, we're pretty comfortable using scientific drilling to get down into oceanic crust 1.5 kilometers. The deepest, you know, continental borehole is 10 kilometers, right? The problem is, how do we attack these thickly sedimented basins? They're really interesting systems. The Gulf of Mexico is more, it's more tractable, and even there it's kind of intractable because, you know, how would you attack this problem of the effects of metamorphism? Because it's going to set up a whole fluid system, right? We sort of focus on the brines that are up in the oil window, but you know, that's at 130 degrees centigrade. We're talking about fluids at 500, 400, 300 degrees centigrade. And nobody has got a clue how that system works because we've never really attacked it.
But it's probably worthwhile to understand it because it may be critical to how subduction is initiated, right?
Yeah, well, there is always that question of how the, you know, implicit in subduction initiation models for a lot of people is the idea that passive margins turns into subduction zones. And there are very few examples of that in the geologic record. So it's a deeply held opinion that isn't supported by geologic evidence. You know, so that has to be dealt with. But regardless of subduction initiation, these thickly sedimented basins are going to be a really important and interesting scientific problem for the 21st century. You know, that's clear to me. How you study them is another question.
Okay, are there any other questions or comments out there?
I have a question.
Okay, please.
Yeah, hello. I'm Joby. Can you hear me?
Yes, I can hear you.
Yeah, thanks for your presentation. Yeah, I'm a PhD geophysics student, and I'd like to ask 2 questions about your first interferometry method presentation. So, yeah, I think seismic noise interferometry solution can be efficient and beneficial, but I think if we want to extend this approach to solve any other problems, for example, you suggested application in hydrocarbon reservoirs and 4D timeless monitoring. I think the vertical and horizontal resolution are important to the extension of your approach. So could you give any comments about the vertical and horizontal resolution of your method?
Yeah, it's usually insufficient. So for imaging purposes, I think it's going to have to be a complement. Maybe it could be a first pass survey to determine whether or not it's worth hauling out the heavy equipment and the big budget, or it could be incorporated to extend the frequency range of whatever source or the utility of whatever source you do use. Thinking now, I'm not sure I was clear about that particular slide where I claim you could use this for all sorts of applications. I was actually talking about that array in particular. It's a array with its own computational capacity. And so you can locate earthquakes like aftershocks automatically. You could locate microseisms automatically and build a data set like that. It does the first pass. So I wasn't necessarily talking about seismic interferometry for all of those different applications. But you're right, for imaging, it's problematic because you're at I did have that slide there where I talked about one of the limitations is the frequency content of the waves that are provided to us by the Earth. It's usually not what we want.
Yeah, thank you. I have the other questions about the machine learning application. I think you have used the k-mean clustering techniques for your interferometry project, but do you have any ideas to improve the other steps in your interferometry research? For example, I think the spectral enhancement by using the machine learning, the spectral enhancement of your seismic noise data will be very helpful to extend the hydrocarbon reservoir and void timeless monitoring applications. So, do you have any ideas to integrate your seismic interferometry method with machine learning techniques?
With what learning?
Do you have any ideas or comments to integrate the machine learning techniques with your interferometry method?
I'm leaving that to the students. I really don't. It's not my bag. And it was Joseph who initiated this project with the k-means clustering. That's really just dipping our toe into it. I'm sure there's a lot more to be done. I think it's hopeful. I think that's what we showed, is that it's hopeful, but what we did was really elementary.
Oh, okay, thank you so much.
And I guess I might as well point out, since no one else has brought it up, that this issue about assessing convergence in real time and then deciding when we can pack up and go home early, we never solved that problem. What we did was we collected data for a certain amount of time, and then we tried to reproduce it by, stepping along and processing the first day, the second day, the third day, and everything. But what we found most successful was assessing the entire data set that we collected for the entire amount of time that we had available to us, and then cherry picking, with a number of quantitative measures, the best ones to stack. And so that's not the same as being able to record for a day and then decide, hey, if we stay here for another 3 weeks, we're not going to do any better. We got it all done in a day. That's what I was hoping we would be able to solve, or that's the problem that needs to be solved. And we didn't solve that problem.
Okay. Well, Jay, I wanted to thank you very much for your taking the time here to give us two really interesting talks.
It's my pleasure.
I think the experiment of talking about two widely separate topics was a success. So I want to thank you for that. And unless there's any other comments or questions, we'll let you go for this week.
Okay.
I did want to announce that next week we'll have Zhang Lu from SMU, who's going to talk to us about the Aleutian volcanoes. So that'll be next Thursday, November 11th. So be on the lookout for the link for that. But again, Jay, thanks so much. And
it's my pleasure. Hang on just a second, though. Is it possible that the three of you could stick around and we could just talk for just a couple of minutes?
Sure.
I'm game.
Yeah, absolutely. Absolutely.
If you don't have any other business to take care of.
No, I think that's it.
Just a couple minutes. We can schedule.
Sure. No problem. All right, everyone. We'll see you next week. And Saloa, you can stop recording now if you would.
Thank you.
Thank you, Saloa.
Yeah, since Jay is the host, I think he has to stop the recording.
Yeah. Okay, Jay, if you'll just click off the...
Oh, actually, no, I see it now.
Recording stopped.
There we go.
Okay.
All good.
Okay.
Bye.
Bye, Saloa. All right. Thanks, Ning.
Thank you all for coming.